So, for basically just completeness, I wanted to talk about light energy or radiant energy. We've kind of talked about thermal energy, we've kind of talked about nuclear energy, we've talked about kinetic energy, potential energy. I guess in order to have total completeness, excuse me, we would have to talk about chemical energy, but in a sense, we kind of already did when we talked about nuclear energy. Not so much, but kind of did. The next section, the modern forces or the field forces, we talk about electrostatic energy. We talk about, excuse me, gravitational energy, big time gravitational energy between planets and that sort of stuff. But in order to complete the discussion of energy, it's important to talk about radiant energy, talking about light energy. So the energy that's associated with the small section of light, and that small section of light has a name. We call it a photon. The word photon basically is referring to a packet of light. Okay, so when you talk about light and we talk about photons, we're talking about small packets of light, just a small packet of light, basically. So the equation for the energy of a small packet of light is equal to h, which I'll explain to you in a second, times the frequency of light, or it's sometimes expressed as this times the wavelength of light divided by the speed of light. That h is what's known as Planck's constant. It's one of the universal constants. In the next chapter, we'll talk about K, we'll talk about G, and these universal constants, these constants that are supposed to be universal everywhere. It turns out that this h, this Planck length, is another one of those constants. It's basically the basement level of your measurements in length. Okay, to measure something to a Planck length is measuring the very smallest possible measurement of a length. You can't get any smaller than that. It turns out when you start looking at the subatomic and the atomic world, there's a floor, and that length is no longer continuous. And what I mean by continuous is if I think about it this way, that there's every point in between here and here, okay, continuous. When you look at things subatomically, it turns out that it's not. You have a chunk here, 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 here. It's kind of pixelated, if you will. So that h is referring to the Planck length, that basement level, and it's a funky unit, to be honest, but that's basically the way it's always been described to me, as being this basement unit. Okay, so the energy of a single photon, a single piece of light, is equal to that. So the cool thing about that equation is that this is a constant. It's a universal constant. No matter where you go or what you do, it's still a Planck length. So that means the energy of light is based strictly on its frequency. So a piece of light that has an incredibly high frequency has high energy. A piece of light that has low frequency has low energy. So when we're referring to frequency, remember we're talking cycles per second. So how fast it goes up and down is the expression of its energy. Not the linear motion, but how fast it's going up and down. Okay? Does that seem kind of cool? So that's the energy equation. Now you could take this one step further. So I have this idea that E is equal to the Planck length times, excuse me, my brain is gone, times frequency. This equation is doing a substitution, just saying, oh, look, we can say frequency and wavelength is equal to the speed of light. And at that point, we can do a substitution for frequency. But like I said, that is the energy equation for that. One thing that you can do from this is, if you remember, there's an equation for momentum and energy. There's this relationship between a momentum and energy. So that means that when we talk about light, that there has to be a relationship between the energy of light and the momentum of light. So that's kind of an interesting thought about it. If you think about it, that light has momentum, but it doesn't have any mass. So it has this momentum, this intrinsic property for an object to continue to move in that direction. So theoretically, you could be hit with enough light and it would push you across the room. It would be an awful lot of light, to be honest, and your body would probably absorb a great portion of that, and you'd probably bake like a chicken. So not something you really want to do. But it also, that idea of momentum is also what leads NASA to think about building solar cells, and they have a plasma-based solar cell called M2P2 that I kind of was kind of hip. I don't know if they're still interested in it, but it's capturing the momentum of light to propel that object out, further and further outwards. The advantage of something like that is that when you're talking about an spacecraft, is that most our traditional way of thinking about spacecraft is that it can only produce an acceleration as long as it has fuel. Once you burn out your fuel, you no longer have an acceleration. When you talk about solar cell technology, it'll accelerate as long as it has sunlight. So as long as it's experiencing light, it should continue to accelerate. So theoretically, it can accelerate the entire length of our solar system, and then maybe a little bit beyond. I mean, mind you, when you're hitting Uranus and Neptune, your sunlight is greatly diminished, but you're still getting some. You're still experiencing an acceleration from that. Cool? Anyway, that was kind of a tangent. I just wanted to go off on that one. So that's the relationship between energy and light. Cool? All right.